All right, so electrons in atoms and the periodic table. So Hindenburg was a famous accident where a giant blimp full of helium, or sorry, not helium, hydrogen, burst into flames and killed 36 of the 97 passengers. But what is it that made the hydrogen so reactive and flammable? And why is helium, which hydrogen's got, one proton, helium's only got 4 protons, why are those so different? Right? If the Hindenburg was made of helium, it wouldn't have burst into flames. We'll see that comes out of the electrons. So modern blimps, of course, then are filled with helium, and they're not just sort of one giant balloon. There are a bunch of little balloons inside of a giant balloon to hold them up. But helium's inert, so it can't catch on fire. It's also somewhat of a limited resource. But we're going to learn models actually that explain why helium's inert while hydrogen is reactive. So are other elements as reactive as hydrogen? Yes, also the other group 1 elements. So we talked about the periodic table and how it is fairly remarkable that when it's arranged this way, it explains, or it has trends in the periodic table, right? So everything in group 1 is really reactive, highly reactive. Group 2 is also reactive. And then helium is in the column with the noble gases, which were all non-reactive. So these models and theories help explain the observed behaviors of groups of elements. So why is it that when we arrange the periodic table in this way, that these elements are similar? We're going to look at 2 models. I think we talked about the Bohr model already, maybe? Talked about the plum pudding model and how that wasn't accurate. We'll also talk a little bit about the quantum mechanical model that both propose explanations for the inertness of helium, the reactivity of hydrogen, and the periodic law, which is the trends that emerge when you arrange the periodic table in the way that it is. These models also explain how electrons exist in atoms and how those electrons affect the chemical and physical properties of elements. And a lot of this is going to be, we talk about quantitative versus qualitative. So quantitative is like the quantity of things, right? It's working with exact numbers. Chapter 8 was sort of quantitative chemical reactions. A lot of what I'm going to expect you to learn for chapter 9 is going to be qualitative. So it's the quality of things. Not as many numbers to deal with. Anyone who is not shocked by quantum mechanics has not understood it, said by Niels Bohr. Erwin Schrödinger, of the famous Schrödinger's cat, said, "I don't like it, and I'm sorry I ever had anything to do with it." Then Albert Einstein said, "God does not play dice with the universe." Most of that is with regards to quantum mechanics, which when you get down to small enough particles, even smaller than atoms, the rules that we follow as macro scale beings fall apart. And that's what they're talking about here. For example, you get electrons traveling through solid objects. Actually, it's quantum tunneling that lets the solid state storage in your phones work. So the quantum mechanical model of the atom is foundational to modern chemistry. This is our best understanding, the best understanding that we currently have, and explains the most things. It forms the basis of the modern periodic table, guides our understanding of chemical bonding, which I alluded to earlier. And applications include semiconductor devices, as I just mentioned. Solid state flash storage uses quantum tunneling to put electrons in little bins and then remove them out of those bins, and your phone reads that as pictures of your cat or dog. And also the design of new drugs. So figuring out how things interact can let us design new drugs. Where we're going to start in this sort of approach towards this quantum mechanical model is with electromagnetic radiation. So all forms of light are electromagnetic radiation, all the way from radio waves to even gamma rays, right, the toxic, or not the toxic, the deadly product of nuclear fission. They're all forms of light. So light is a form of electromagnetic radiation. Light is not matter. It's really energy in motion. Light is a type of energy that travels through space at a constant speed of 3 × 10⁸ meters per second, or 186,000 miles per second. Remember, the distance to the moon is 240,000 miles. So it takes just over a second for light to get from Earth to the moon, and then just over another second to get back. So light has properties of both waves and particles, and that's one of the things that confused scientists for so long. You thought you could be one or the other. Light somehow does both in certain ways. So as an analogy, when you disturb the surface or the surface of water, it creates waves. If it's still enough, you can see those waves, and they travel outward from that site. Because this is like turning on your flash in the middle of the night, but in super, super, super slow motion. Right? The light from the flash on your phone, to us, is instantaneous. But it is taking time to travel, and it travels in the form of a wave. So we have a few different parameters that we use to describe these waves. One of them is the wavelength. So the wavelength is the distance between adjacent wave crests. So if you measure from a high point here to a high point here, that's the wavelength. Simple enough. For visible light, wavelength determines color. So if you ever tried to buy a laser pointer, it's actually way, way harder to buy laser pointers now. You used to be able to you still can, but they're harder to find. You get really, really cheap ones from China, and they take a month to get here, but you can get blue ones, red ones, and green ones, the sort of primary colors that you can get. And those each have a different wavelength of light that they produce. And lasers are cool because they produce a single wavelength, if they're a good laser. So they're producing light with a set distance between those crests. White light that we see and is most of the things that we, or most of the lights that we have in our houses, is actually a combination of all of the colors of light. So if you took all the wavelengths of visible light, you get almost all of them from, especially something like these fluorescent lights. They produce a very white light. Should have brought a prism. But if you have a prism, you can actually separate all the wavelengths out. And you can see each wavelength individually. And if you have the right instrumentation, you can measure the intensity of those individual wavelengths. And actually, if you've bought light bulbs before, you know you can get like warmer lights or cooler lights. And they are measured by temperature. I don't know if you've noticed this. It's like 2,700 Kelvin. I believe that is related to the quality of light of a tungsten filament at that temperature. It's something like that. So if you actually heat metal up, it produces whiter and whiter light as it gets hotter and hotter. Actually, more to red light as it gets hotter. Cooler lights are more blue. Anyways. So we can take this light and we can split it into individual colors. And one of the trippy things about color of things is that a red shirt appears red because it's reflecting red light only. So if something is red, that means it's absorbing all the other wavelengths of light. So the best light for plants to photosynthesize is not green, but it's all of the other colors than green. Because in nature, aside from light reflected by plants, there isn't very much green light. So the color that you see on something is the color that it's reflecting. And actually, I'm going to have so many asides because I think electromagnetic radiation and light are really cool. The butterfly wings are not actually blue. If you see a butterfly wing and it looks blue, it's not actually blue. What's happening is the light is hitting the scales on the butterfly wing, and the distance between those scales is I think it's the distance of blue light. So when you have a prism, it reflects into all the lights. The scales on a butterfly wing are basically a prism selective for blue light. That's why they look blue.
Is that the same for feathers on birds?
Not necessarily. It might be, but not in general. So one of the other things that we use for describing a wave is frequency. So before we saw a wave, actually let me draw a different wave. So if you have a wave like this traveling through the air in this direction, the frequency is the number of crests that pass through a stationary point in 1 second. So if a wave is traveling forward like this, you could measure how many of those crests pass in a second, and you would be measuring the frequency of the light. And then because light is always moving at the same speed, the wavelength determines or is inversely related to the frequency. So if you have a wave where the crests are really close together, since it's moving at the same speed, you're going to have more crests passing a point in 1 second versus a wavelength that has a long wavelength, fewer crests will pass in a second. So the shorter the wavelength, higher the frequency. So as mentioned before, light has particle and wave properties. You can think of it as a stream of particles. Those particles are called photons. So a photon is a particle of light, like a single packet of light energy. The amount of energy carried in the light packet on the wavelength, or depends on the wavelength of the light. So if you have a short wavelength, higher energy. If you have a long wavelength, lower energy. This is the kind of qualitative assessment kind of question that I would ask you. Right? I give you a list of wavelengths and say which of these is the highest energy. So if we had wavelengths of like 1 meter, 0.1 meters, 0.01 meters, which of those wavelengths, lambda's wavelength? Hold on. Better get that right. Yeah, lambda's wavelength. Okay. Let's double check. So if we have these different wavelengths, which of these wavelengths has the highest energy? 0.01. Right. Now, which of these would have the highest frequency?
1.
No, 0.01, right? Shorter wavelength, higher frequency. So light waves carry more energy if their crests are close together. I like to think about this too as like waves crashing on the beach. Be a lot more energy if the waves were crashing faster.
Are the wavelengths always going to be the same size?
For a particular energy of light, the wavelengths are always the same size. So wavelength with frequency and energy are all tied together. So like visible light, or if you have a laser pointer, we'll get into wavelengths or frequencies of light related to energy later, but red laser pointers have the lowest energy because they have the longest wavelength, and therefore the lowest frequency. Oh, well, it's right here. So long wavelength, low frequency, low energy. Actually, you can think about this as, so long wavelength, low frequency, low energy, all L's. Doesn't quite carry over for short wavelength, but short wavelength means high frequency, high energy. So this is the electromagnetic spectrum. And the way that this is set up here is that all of these frequencies of visible light, or actually they're done by wavelengths, so all these wavelengths of visible light are actually a very, very tiny portion that exists right here. So the spectrum of visible light exists in this tiny little band, and then everything else is outside of that. So if we have a long wavelength. It's over here too. So these are, wavelengths. Long wavelength, 10 to the 5 meters, very, very long wavelength. Those would be like the longest wavelength radio waves. So radio waves are super, super low energy. Microwaves are actually one of the second lowest energy wavelengths. The reason that microwaves can heat up your food is because they happen to be the same frequency as, I believe, one of the vibrational modes of water. So temperature is related to the energy of individual molecules. And so when you hit water with microwave radiation, it, in particular, excites water molecules. So, yeah. Infrared radiation comes after that. Then we have the visible light spectrum. Then it's UV radiation, the different types of which can cause skin cancer and sunburns. Going higher than that is X-rays, and then gamma rays, which are the highest energy radiation. So again, a question I would ask here would be, I'd say between radio waves, microwaves, and infrared radiation, which of these is the highest energy? Or which of these has the longest wavelength? Or the longest, wavelength, frequency, energy, right? I could ask any of those questions for that. So gamma rays are our shortest wavelength, most energetic. They're produced by the sun, stars, and certain unstable atomic nuclei on Earth. X-rays can pass through many solid substances. We use them as in medical devices for destroying tumors and for imaging, because if you pass X-rays through your arm or through your body, your bones are more dense and will block more of the X-rays than the rest of your flesh will. And so they'll pass right through. So X-ray or gamma ray beams can be aimed at cancerous tumors. I think this is really, really cool. One of the ways you can do it is you pass really weak beams of radiation from multiple directions, so that wherever they cross is receiving a very high dose of radiation, but everything around it receives a very low dose of radiation. You can do this X-rays or gamma rays. So those gamma rays can then damage the tumor cells, and they're specifically the genetic material, so they can't reproduce, and the tumor dies. It does do damage to healthy cells also, but when you've gotten to this point, that's a loss you can take versus getting rid of the tumor. Ultraviolet light or UV light is the component of sunlight that produces sunburn or suntan, if you get just the right amount. They're less energetic than X-rays, but still damaging to biological molecules, but they don't pass through you to do damage inside of your body, just on the surface. And they're pretty easily blocked. And then visible light does not damage biological molecules, but really cool, it does rearrange molecules in your eye, which creates a signal which your brain interprets as vision. So if you don't know, there are 3 cones in your eyes, one each for the red, green, and blue light. I am just a tiny bit colorblind, so my green cone is a little bit messed up, a little bit mutated. You can have people with 4 cones who can apparently see billions and billions of colors more than everybody else. I can imagine like color matching walls would be a nightmare. Can never get it quite right. What else was I going to say about eyes? Oh, just that the color, was it magenta, doesn't exist, because all of the colors that we see are combinations of various frequencies. So red and blue are at opposite ends of the spectrum. So if our brain sees red and blue light at the same time, it makes up a color to fit in the space in between. Yeah?
So what causes people to choose 2 different colors if they're looking at the same one? Because you said, how you're kind of colorblind, so you can't really see green, you said?
Oh, I'm just a little bit colorblind, but
Well,
Yeah. You can be completely colorblind. No, it's okay.
But you know how they had that picture of the dress on social media and people were saying,
Oh, yes. That's a completely different thing. Has to do more with how your brain interprets colors, because I did just fairly recently see a TikTok where they were looking at this exact kind of thing. And she had this painting of a person, digital painting. So she sampled the color off of it's like a woman on a black background. And she sampled like a piece of her arm, which looks like skin tone. And then she painted it somewhere else, and it's completely gray. And then the woman was wearing a gold dress, so she sampled the gold dress, and then she painted it somewhere else, and it was there was no gold in it at all. It's a completely different color without the context. So another crazy thing that our brain does is it interprets the colors based on the colors around it. So that's how you get a lot of those visual illusions, where you'll have a gray background with black squares, and your brain sees dark circles at the corners of the squares that aren't there. So if you look at the squares, you see the circles. If you look at the circle, it disappears. So yeah, that can happen, but it's all how your brain processes it. Right? Electromagnetic radiation is cool. Infrared light, I think, is really cool because it's actually heat. So what you feel is heat from a campfire is infrared radiation. All warm objects, including human bodies, emit infrared light. Infrared sensors are used in night vision technology to see in the dark. But really all it's doing is translating infrared into visible so we can see it. The James Webb Space Telescope that just went up is actually an infrared telescope to look into the deep, super old universe. But they had to build a special sun shield to block it from the Earth and the sun and any infrared radiation nearby so that it could actually see past that. Because everything that's warm emits infrared light. So here's an example of an infrared photograph. This is one that's colorized, so you can see the different temperatures. So everywhere that's blue is a cooler temperature. Places that are red are the hottest. Well, white's the hottest. So you can see temperature that way. So now we're moving past that to even lower energy. We have microwaves, which are used for radar and in microwave ovens. The reason they heat water is because water efficiently absorbs the energy from microwaves. Radio waves are used to transmit the signals used by AM and FM radio, cellular telephones. Sorry, this slide is old. I love the phrase cellular telephones. Cell phones, television, and other forms of communication. Bluetooth, that kind of thing. Okay, so if we've got these visible colors of light, we've got green, red, and blue. In order of increasing wavelength, what order would we put them? So if we're thinking about wavelength,
Red is first for increasing rate.
for increasing wavelength, I even have to think about it a little bit. Red actually has the longest wavelength. So increasing would be shortest to longest. So blue would be first. So we'll go blue would have a shorter wavelength than green. And then green has a shorter wavelength than red. Okay, if we have the wavelength now, what is the frequency order? So we want the increasing with the shortest frequency first. No, it's blue. Wait, yeah, it's the same. Yeah, because blue would have the, well, hold on. Blue has the highest frequency, shortest frequency, yeah. Sorry. Green, and then red. And then the energy per photon. It's the same again, yeah. Green, and then red.
Okay, wait, you're saying, so the blue is the what?
Blue has the shortest wavelength.
Oh, I see. I'm going this way, but it's this way. Okay, got it.
Yeah, shortest wavelength is the highest frequency. I guess that's the one that, yeah, because I said the shortest frequency,
Yeah.
the shortest duration between things. But frequency would be number of.
So it's switched, right?
So if you think of it as, yeah,
Red, green, blue.
it is switched. So it felt off. So it should be red, green, blue. Because red has a long wavelength, which means it has a low frequency, L and L. Blue has a high frequency, so it's a short wavelength. Yeah. Oh, I should have put this on this. Should have put those on this slide. Okay, so now jumping into the Bohr atom, or the Bohr model of the atom, right? Because we talked about our ultimate goal is we're going to get to the quantum mechanical model of the atom. But we had to start by talking about electromagnetic energy, because one of the first ways that scientists sort of peered into how the electrons were working was by, not heating up, but passing electricity through gases. So neon atoms inside glass tubes, right? They're absorbing electrical energy and then emitting that as light. Right? Those are neon lights. But different elements have different colors. So a mercury lamp makes like a blue, and a hydrogen lamp appears pink. So if we take actually the light emitted by hydrogen and we pass that through a prism without any white light from surroundings, you get very specific wavelengths. Remember, if you pass white light from something like these lamps through a prism, you'll get the entire spectrum. So this entire thing that's mostly dark here, actually, hopefully you can even see it. Yeah. There's another line at the top there too. So that hydrogen lamp is only producing these 3 frequencies of light, or visible light at least. So that led scientists to believe that something was going on here that could explain those exact 3 frequencies, or wavelengths. So again, white light spectrum, right, completely filled up, all the different wavelengths of color. The hydrogen light spectrum has 3. Helium adds a couple more. Oh, actually, there's one there that you might not be able to see at the far end of violet. But these are the emission spectrums for each of these elements. And they emit light at certain wavelengths. You can actually use this to identify different elements. So the question is, why do excited atoms only emit light at particular wavelengths? At the time, Niels Bohr developed a model to explain this. He said, well, if it's the electrons around, because they knew about electrons, but if the electrons around it can sort of jump to certain energy levels, and only those energy levels, then maybe it's the electrons being excited by the electricity, jumping up to one of these levels, and then as it falls back down, it releases that energy as specific frequencies of light. So for a very simple atom, you might have something that looks like this with 5 different frequencies of light, or 5 different orbits, 5 frequencies. This idea that you can only jump to certain steps is called quantization, or you could say that the energy here is quantized. So it's like this ladder that has rungs that are unevenly spaced. Right? On a ladder, you can only step up to the next rung or down a rung. You can't be anywhere, can't stand on anything in between. So orbits, and actually this is a key thing. The Bohr model talks about orbits. The orbits are specified by a quantum number. And because you can only have certain levels, think of it as just the first rung on the ladder, the second rung on the ladder, third, and so on. Right? So higher energy, higher number, each one is describing an orbit. And it's impossible for an electron to exist between orbits. So you can only be in one place or the other. So Bohr model worked for hydrogen. When a hydrogen atom absorbs energy, we get an electron excited up to a higher energy orbit. As it relaxes back down, it emits a photon, remember, which is a packet of light, at a specific wavelength in proportion to the amount of energy that it took. So if it jumps up to 1 and then back down, you're going to get a longer wavelength light, lower energy light. So there's excitation and relaxation. So light emitted by excited atoms consists of specific lines at specific wavelengths, and each one corresponds to one of these quantum orbits. So you could explain the frequencies of light for a hydrogen atom as these electrons jumping up to the third, fourth, and fifth orbits, and then relaxing back down to produce the very specific wavelengths of light. Did I put it in here? Okay, yeah. At Reedley College, they had this set up actually. So this is a fancy prism. On the left, okay, why did it do that? Nope, okay. So the light on the right, this is super annoying. This light on the right is, what the hell? I want to write. Okay, there we go. So this is what a hydrogen lamp looks like. It emits this like pink light. And then this is split out from that, well, on a prism to give you, there's one, it's very faint blue, then there's a green, sort of bluish green, and then a red. And then the second one, I think this is helium. This is a blue light, and you have more, but still not a ton of different frequencies. And then this is neon. So as our atoms get more complex, as they grow in size, we're also adding electrons. So all of those electrons can jump to different places. So the Bohr model had great success with hydrogen, but it couldn't predict the emission spectra of other elements that contained more than one electron. If you remember, hydrogen, periodic table, it has one proton, and it has one electron. So for every element on the periodic table, if they have zero charge, they have the same number of electrons as they do protons. So if we jump from hydrogen to helium, we have 2 electrons, and the Bohr model couldn't even explain the spectrum of helium. So there was some piece missing. There was something missing from this scientific theory. And that's the quantum mechanical model. So one of the key things in the quantum mechanical model, which replaced the Bohr model in the early 20th century, it didn't treat electrons like particles flying through space. So in the Bohr model, there's very literally an atom, nucleus, right, where the protons and neutrons are, and then I should have the Jimmy Neutron logo in here, right? So then electrons would be spinning around the outside on set paths. Well, the quantum mechanical model said that's not it. It doesn't actually look like that. And so it replaced these specific orbits, which are like a path where you'd have like an electron, like the moon, orbiting, with quantum mechanical orbitals. So they thought they were fancy, they changed the end a little bit. An orbital is a probability map. So it's basically, it is a statistical distribution of where the electron is likely to be found. So rather than being this set path, they said it's a cloud. So to sort of help visualize this idea of like statistical probability maps, you can think of a baseball being like an electron. So baseball's path can be easily traced as it travels from the pitcher to the catcher. And if an electron, oh, this is the slide I was thinking of. Okay. The difference between a baseball and an electron, if we're thinking of them as the same thing, Niels Bohr said if you throw an electron, it'll travel the same path every time, just like a baseball. In reality, even if you throw that electron the same way every single time, it ends up in a different spot, unlike the baseball. So it's sort of the difference between an orbital and an orbit. So instead of thinking of this baseball thrown this way, imagine you have like a really, really good pitching machine, right? Pitches it in the exact same spot every time. Would be like me throwing a baseball. And actually, this wouldn't be like me. This would be like somebody who's good at baseball. When the pitcher throws it, it ends up in maybe the strike zone most of the time. We'll say 20% of the time ends up right in the strike zone. 40% of the time it ends up a little bit outside, so wider strike zone maybe. And then total of 70% of the time, it would land in this wider area. So you're most likely to find it or have a pitch in the center, but the electron can be anywhere inside the space. So you'd have to throw a bunch of electrons and see where they end up. So the key difference to understand here, though, is that an orbit is predictable, and an orbital is completely unpredictable. It was actually Erwin Schrödinger came up with the thought experiment of putting a cat in a box. Schrödinger's cat is a thought experiment for this property of electrons. If you do all of the math, which he had done, basically you can either know exactly where an electron is, or you can know how much energy it has. You can't know both. Because as you solve for one of those variables, the other one becomes completely uncertain. But the process of looking at it changes the value. So orbitals are specified with a number and a letter. The number is called the principal quantum number and specifies the principal shell of the orbital. So you can think of this as sort of like the energy levels that Niels Bohr proposed. We still have something like that, but now we also have subshells. So these are the probabilities of where the electrons can be. So principal quantum number, which would be n, and then our subshells, which are letters of S, P, D, and F. One of those four. So the 1s orbital is the lowest energy orbital. Orbitals exist in 3 dimensions. So if you look at this, we have x, y, and z axes, which means that it's a sphere. So as you can think of this as kind of like a bubble, and the electron is 99% of the time, well, probably 90% of the time inside of that sphere. So this would be like taking a photograph of an electron every second for 10 minutes. You'd catch it in each of these, or in a spot, put all those pictures together, and you'd see all of the places where it's probably going to be. So dot density here also represents probability. So if you look at just a section on the outside here, not very dense. As you move towards the center, these dots are closer and closer together, indicating that you're more likely to find an electron there. Also, please stop me if you have questions at any point. We're about to get into practical application of this. So we represent these orbitals as geometric shapes. This one is the sphere. S orbitals are spherical. So that sphere represents the volume within the electron is found 90% of the time. 10% of the time it won't be in there, but 90% of the time. It's pretty good. So the single electron of an undisturbed hydrogen atom, so one single hydrogen atom hanging out by itself at room temperature, that electron is in the 1s orbital. It's called the ground state, or the lowest energy state. And generally, electrons will try to be in the lowest energy state possible. If something causes that electron or that hydrogen atom, and the electron specifically around that hydrogen atom, to absorb energy, it'll cause it to jump to a higher energy orbital, which is called an excited state. And because electrons want low energy, that excited state is unstable, and that electron will release a photon to get back to the ground state. So for each atom, we have one ground state, it's lowest energy, that's where it's chilling, and many excited states. So there are many possibilities for those electrons to jump up to higher energy levels, only one low spot that they want to get back to. So the n equals 1 principal shell contains one subshell S. And the n equals 2 principal shell contains two subshells, S and P. The 2s orbital is higher in energy and slightly larger than the 1s orbital. So basically, take our 1s, make it a little bigger. So every time you jump up one of these energy levels, or principal shells, your orbital gets bigger. So like I mentioned, the n equals 2 well, it's not an orbital. What does it say? Principal shell, that's what I'm looking for. N equals 2 principal shell has two different types of orbitals. So 1s is the sphere, 2s is a slightly larger sphere, 2p is this dumbbell shape. And so those each exist on a different axis and represent where the electron could be if it's in that orbital. So it's all the same shape, but just different orientations. And these all came out, like somebody did a bunch of math and figured out these shapes, which I think is wild. So the number of subshells in a given principal shell is also equal to n. So as we move up from up in energy level from 1 to 2 to 3 to 4, we have one type of subshell, two types of subshells, three types of subshells, and four types of subshells. So in the n equals 3 principal shell, contains subshells specified by S, P, and now D. The D subshells have, D subshells contain 5 different orbitals. So kind of jump in odd numbers in terms of the orbitals that we have. It goes from 1 to 3 to 5, and then it does go to 7 And then I think 9, because I think there is another one after that. But the s and p subshells contain 3 s and 3 p orbitals. So every time you move up, so if we go from n equals 1, we'll have 1s. If we go to n equals 2, now we have 2s and 2p. N equals 3 is 3s, 3p, 3d. So you can kind of think about these as addresses for the individual types of orbitals. Gives you the energy level and the shape. And every time we're getting slightly larger, slightly more energy. So the p subshells, or the p orbitals, were the dumbbells. There are 3 of them. The d orbitals are these sort of cross-shaped dumbbells. So each one has 2 dumbbells that are crossing. And they exist in, let's see, is that 1, 2, 3, 4 different planes. And then there's the special dumbbell with the donut. This is an interesting shape because that donut that's around the center there doesn't touch the other 2 orbitals, or the other 2 parts of the orbital. So you can have an electron traveling from, well, let's just say, from here to here, and it does not pass through the space in between. It just goes from one point to the other. This is why, like, in the Marvel movies, when they're like, the quantum realm is like super weird and has no rules. I mean, it has rules, but they're super weird. So it's like, they got that right at least. Time may not mean anything if you're at that size. So we can move between any of the orbitals without passing any of the spaces in between. All right, now this is the application of this chapter. Aside from sort of the definitions of things throughout, the electron configuration shows the occupation of orbitals by electrons for a particular atom. So for the ground state hydrogen atom, we have 1s1. And that's 1s with the 1 as a superscript, telling us that we have 1 electron in the 1s orbital. Ground state hydrogen. And we'll only calculate these for ground state atoms. So if that's our, electron configuration, then the orbital diagram gives us similar information, but shows the electrons as arrows in a box representing the orbital. So here we have, again, 1s, right, same orbital, but this arrow is our 1 electron. So you can have those arrows be either up or down. Whenever you write them together, they pair up. 1 is up, 1 is down. It's called their spin. We won't talk about that much, but when you're writing them out, they need to be alternate spins.
So that in the box, that's an arrow?
Yeah, that's like a half up arrow. Yes. Yeah, no. Could be, yeah. I see that. The arrow represents 1 electron. Yeah, so if we wanted to do helium, you'd have a box. And this would be 1s, yeah, and you'd have 1 up, 1 down. Oh, there it is. So in orbitals, the direction of the arrow represents the electron's spin, which is a fundamental property of electrons. The Pauli exclusion principle is that orbitals may hold no more than 2 electrons with opposing spins. So you can't put more than 2 electrons inside of an orbital, and they have to have opposite spins. So again, if we do helium, we have 1 electron, 2 electrons. No more than that. If you have more electrons, they go to the next orbital. Well, we've already seen this for helium, but we'll do it again. So for helium, the electron configuration is just the address. So for helium, Again, helium has 2 electrons. So we can fit all of those electron configuration first is what I'm doing. So 1s2. In the 1s orbital, we have 2 electrons. Because helium has 2 electrons, and we'll fill all of our orbitals essentially from the lowest energy state up to the highest energy state. So the orbital diagram for helium would be a box representing 1s. We'll say you could also represent it as just a line. So that's 1s. And then it has 2 electrons. So I would accept either of those. But you have to have that half up arrow, half down arrow.
Does it matter which way the thing is going?
Oh, the first one could be down and the second one could be up.
No, but like what if I want to go this way?
No, they have to go up and down.
No, I know, it'll go up, but it'll be this way.
Oh, I see. If you
Serious.
if you wanted to do that,
No.
does that not? That's,
No.
oh, you said like this? No. That makes me uncomfortable. That's wrong. Look at how nicely they fit together. Back to back. This is too close to just writing N. Okay. Okay, so for lithium then, how many electrons does lithium have? 3 electrons. So lithium, number 3, has 3 protons, has 3 electrons. So we're going to fill these from the lowest orbital to the highest orbital energy-wise. So we start with 1s. We can only put 2 electrons in there. Then we move to the next highest energy orbital, which is 2s. And we put our last electron there. So 1s2, 2s1. Then for our orbital diagram, actually I'm going to do this with just the line. We'd have 1s and then 2s, which I know because we're going to fill this one up. That's 1 and 2. And then our third electron is by itself in the 2s orbital.
I'm curious how you deal with the square. Would it be two different squares?
2 different
I
squares.
tried doing like, kind of like the orbits, the square inside square.
Yeah. Okay. We'll get to why you do need to separate them.
Okay, cool. Gotcha.
Because if you have, once we get to P, it has 3 orbitals, and so we'll put those 3 boxes if you did boxes together. Okay, so that's how you would write electron configurations, orbital diagrams for helium and lithium. So we fill from lowest energy to highest energy, and this is just a diagram to see all of those laid out next to each other. So 1s is the lowest. So you put electrons there first, then they overflow into 2s, then you go to 2p, so there's 3 orbitals there, 3s, 3p, and then it gets a little bit weird because the energy levels are such that 4s is actually lower energy than 3d. So because 4s is lower, instead of filling straight from 3p, if we had more electrons, we would put them into 4s first. And then we'd move up to 3d. So you're moving up higher and higher energy. Okay, so let's write the electron configuration and orbital diagram for carbon. So how many electrons does carbon have? 6. So we'll start writing these out. And again, we're just always starting with the lowest one. So 1s, 2, 2s, 2. And then we move over to 2p. 2 electrons left, so 2 electrons go into the p orbital. Then for the electron orbital diagram, we'd have 1s, we'd fill that with 2 electrons. We'd have 2s, which would also get 2 electrons. And then we would have 2p, which has 3 orbitals. And then here we have to follow Hund's rule. So when filling orbitals of equal energy, electrons fill singly first and then with, or singly first with parallel spins, and then they'll fill up with opposite spins. So for our last 2 electrons, they'll each get their own orbital, and they'll be in the same direction, spinning in the same direction. So you could put it in the first one and the last one. You could put it in the last 2. Doesn't matter which 2 you fill, it just needs to be separate. Right. Because we used up all of our electrons. Okay. So this is the Quantum Hotel, a discount resort for electrons in Mrs. K's Chemistry Land. So this is my mom's hotel at Chemistry Land. The first floor has 1 room. And we always fill the hotel from the lowest floor to the highest floor. The second floor has 2 rooms, S and P. The third room has 3 rooms, S, P, and D. And then each S room has 1 bed, so they're single bedrooms. P rooms have 3 beds. D rooms have 5 beds, and then F rooms actually have 7 beds. Probably call it more of a suite or a barracks, depending how they're arranged. So our floors are principal shell, room is a subshell, bed is an orbital. Then the people are electrons. So we can only have 2 people per bed, and they have to have opposite spins. I guess they don't want to lay head to head, so they go head to foot on the beds. They're weird like that. But also, if they get a room, so if we fill up a room and the next room has 3 beds, but there's only 2 people staying in it, they're going to pick their own beds. They have to sleep on, hotel rules, you have to sleep with your heads on the same side. If you sleep on opposite beds. No. So if we're filling in electrons, let's do oxygen. So we've got 8 people who are coming to stay at Mrs. K's Chemistry Land. And so we start filling them and checking them into rooms. Hotel's currently empty, so we put the first 2 people in the first room. They have to share a bed. The second 2 people, I guess I should cross these out, get the second floor room, which is 2S. And then we've got 4 people left over. Well, fortunately, room 2P can fit 4 people. So we'll fill these in each with 1 person in each bed, and then they draw straws for who has to double up. So it could be in any of them. It doesn't really, electron could be in any of them, doesn't really matter. Tend to fill it in left to right. So always fill them in, give them their own beds first. I will show you a trick. Tricks. All right. You can use this to figure out how to fill orbitals, because things do get a little bit trickier once you get up to 3D, because it comes after 4S. So up to 3P, you fill everything in the order you would expect. After that, because 3D is higher energy than 4S, you fill 4S first. So this is one of the tricks. If you write out all of the 1s orbitals, and then all of the 2p orbitals, but starting at the same level here, then all the 3s are in a row, and all the 4s, so on and so forth. If you fill in this order 1s, let me draw an arrow here actually. So we fill 1s first, then 2s, then we go 2p, 3s, then we go 3p, and then 4s. So if you follow this pattern, you always fill them in the correct order. And then we go 3d, 4p, 5s, and then it'll be, whoops, 4d, 5p, 6s. So you can keep going through these, and you'll fill them in the right order every time. You can also determine the order from the periodic table. Yeah, you can determine the order from the periodic table. So it gets a little bit off. It gets a little bit wonky. Do I have a periodic table here? Yes, good. Okay, so we talk about s orbitals, p orbitals. Groups 1 and 2 are all the s orbital electrons. Helium technically fits over here with regards to this. Hydrogen and helium are just weird, though. So these are all s block elements. So they all have their highest level electrons in the s block. These are all p block elements, have their highest electrons in the p block, or in the p orbitals. And then these are d block elements that have their highest in the d block. So if we start at the top, we start with 1s, and then we go to 2 and 2s. All right, so this is the 2s. Then these are all p. So we go to 2p, fill all those up. Then we go 3, fill 3s next. Then we go to 3p. And then we go to 4s. The one trick here is that you got to remember that when we start the d orbitals, we start at 3d, not 4d. But then you can keep going, and when you get over here, then our highest energy electrons are in p blocks. So just by looking at something on the periodic table, you can tell where its highest energy electrons are going to be. So if we look at oxygen, actually let me go back to that example of oxygen. We know that it's going to have 4 electrons in the p block because it's 4 elements into the p block. So sulfur also has 4 electrons in the p block. That'll come into play later. Or we could look over at magnesium and know that magnesium has 2 electrons in the s block and nothing in the p block. And if you went down to something like cobalt, it would have, I shouldn't have picked cobalt, 1, 2, 3, 4, 5, 6, 7 electrons in the d block.
Okay, I have a question. Can you go to the periodic? Okay, so when you go 4s, right?
Mm-hmm.
You're going to go 3d.
Yep, 4s1, 4s2.
Yeah, and then you're going to go 3d, you said, right?
Yep.
And then you're going to go to 4p.
Yep.
Okay, now you're going to go to 5s. And then you go, and then...
Then it's 4d.
So
So all the d's are off by one number.
Okay, so 3, 4, 5, 6. Okay.
Yeah.
So 7 would be 6d.
Yes.
7s.
7s, 6d.
Okay.
And we're not going to go that far because then you get into f orbitals. Because then you would go 7s, and then it starts with 7s 61, then it's 7s 62, then 7s 5f, but we don't need to know that.
Okay. I would just...
Yeah. Any questions? Other questions about this? It's all there on the periodic table. So in summary, lower energy orbitals fill before higher energy orbitals, which is why we fill them in that order. Lowest energy on the periodic table just happens to be at the top. We go higher and higher energy as you move down the periodic table. Orbitals can only hold 2 electrons, and when they occupy the same orbital, they have to be in opposite spins. That's the Pauli exclusion principle. And if you have orbitals of identical energy, so like p orbitals or d orbitals, all of your electrons will fill in singly first, so one at a time, and then they'll double up with opposite spins. Let us do one more electron configuration, and actually, we're going to save it because it gets into, because you can imagine, this is the, I'll give you the preview.
What everyone's thinking, so.
I know. I'll give you the preview, the real quick preview. Imagine writing an electron orbital diagram for iodine, right? It's got 53 electrons.
Whoa.
So the next thing that we're going to cover is shortcuts for writing these. Where we basically say, oh, we'll just use krypton, one of the noble gases, as a starting point. And then we basically say, okay, we're starting from krypton. That's 36 of the electrons. And then you just write out in the next row to get to where you want to go. So you can abbreviate. Yeah.
Okay, so I know we didn't finish all of chapter 9, and I know you technically didn't post it, but I see it on my to-do list. So chapter 9 is due on Friday. Do we have to?
Oh, is the chapter 9 homework due on Friday? I'll move it.
Okay, thank you.
Yes. I actually don't think you have anything due Friday. There's no assignments this week. Because there's no lab. There will not be lab on Thursday.